Our goal within this video is to be able to handle systems where there are more than one charge, either in a line or in some two-dimensional arrangement. Before we do that, let's just do a quick review of how to calculate the electrostatic force between two charges, and we'll end up using this value in the next problem. So in this case, we have a 2 microcoulomb and a 9 microcoulomb charge, and they're separated by 9 centimeters. So we would use Coulomb's law. Electrostatic force is Coulomb's constant times the values of the charges. Remember, we don't pay attention to whether they're positive or negative when we're calculating the amount of force, but it's going to come into play in these types of problems in just a second. Coulomb's constant is 9 times 10 to the 9th when we're using standard units. And we will convert our charges to coulombs by multiplying by 10 to the negative 6th. They're both positive, so I didn't have to worry about it. But again, if the charges had been negative, we would have ignored those negative signs. And we're just finding the value or magnitude of the force. And since our distance was given in centimeters, we would divide that by 100 to get 0.09 meters. Make sure that we square that. After using a calculator to figure this all out, we get 20 newtons as this force. Now, that force is the force felt by each of these charges. And since they're positive, it's a repulsive force. So it would mean that the 2 microcoulomb would get pushed to the left, and the 9 microcoulomb would get pushed to the right by equal amounts. It's going to be important to recognize that you can't do this calculation and figure out the direction of the force just from the formula. You have to think about which charge you're focusing on and whether it's an attractive or repulsive force. All right, keep that 20 Newton value in your mind as we go on to the next part. So we have these two same charges, our 2 and our 9 microcoulomb charge, but we've added in a third, a negative 4. That's off to the side. And our goal is to figure out the net force on this charge right here. Okay, so that's our focus. And I like to circle it on my paper if I'm working on paper and really make sure I'm aware of which one that is. So what we want to be noticing here is that this object is going to get pushed away from the 9 microcoulomb like we just showed, but it's actually going to get pulled toward that negative 4. There's going to be an attraction that way. And so we're going to have to take all that into account as we work through this problem. Let's just take this into 2 steps here. You can't do it all in one equation. You need to look at each individual interaction. So first, between the 2 microcoulomb, the one we're interested in, and the 9, remember, we just did this. This came out to be 20 newtons. And we had talked about how the 2 and the 9 push away from each other. And so this is to the left for the charge we're interested in. Again, it's to the right for this one, but I don't care about that right now. I'm only focusing on the one I circled. All right, now we also need to find the force between the 2 microcoulomb and the other charge, the one we added to the system. Let's go through and do that calculation, again using Coulomb's law. I'm not going to write it again since I wrote it on my previous slide. We would take 9 times 10 to the 9th, and we would multiply it by 2 times 10 to the negative 6th, again converting those microcoulombs to coulombs, and then 4 times 10 to the negative 6. Notice I'm not putting in the negative sign for the negative 4. I'm just finding the amount of force. And those two charges are much further apart. They are 12 centimeters away from each other. So dividing by 100, that gives us 0.12 meters. And so when we calculate that, it comes out to be 5 newtons. Okay, so now let's think about the direction for this force. Let me switch to a different color here for a second. Okay, so this is our 5 newtons. That's between these outer charges here, and it's an attractive force because we have a positive and we have a negative. And so the 2 microcoulomb charge is going to get pulled toward the right. Okay, so important to notice that as to which direction, what type of force it is, attraction or repulsion. And so that's the key thing, is then deciding whether to add or subtract. And I like to do a lot of scribbling like this. So I have 20 newtons to the left. I have 5 newtons to the right. You might remember this from first semester. If you have forces pointing in opposite directions, you have to subtract those forces. And so we would end up with 15 newtons. And then we'd want to give a direction to that. And the bigger force is the net force direction. So we would say to the left. Okay, we're going to do another example like this in just a second, so you're going to see it all again. But the key thing is that we had to calculate 2 different values of force and then decide whether to add or subtract them depending on how whether the charges were causing a repulsive force or an attractive force. At the 9 microcoulomb charge now, okay, so we're going to look at this one as our focus instead. And again, we're going to have to calculate 2 forces and then decide whether to add or subtract. All right, well, let's start by looking at the 2 microcoulomb and the 9 microcoulomb. Okay, we've actually already done this. I'll write it out again real quickly here. But this was the force that we just calculated, 9 times 10 to the 9th, and then 2 times 10 to the negative 6th. This is the very first force we found at the beginning. 9 times 10 to the negative 6th. Okay, that's our changing our microcoulombs. And again, these charges are 9 centimeters apart. A lot of 9s in this problem. All right, and that came out to be 20 newtons. Okay, now in the last question, we were focused on this charge over here, and so we were thinking about it being pushed to the left. But now we have our focus on this 9 microcoulomb. It's going to get pushed, but it's going to get pushed to the right. Okay, so it's going to matter, again, which charge we're focusing on. All right, the other force that I'm interested in is between, again, my 9 microcoulomb. That has to always be part of the calculation because that's what the problem is about. But now I'm going to look at the negative 4 microcoulomb. All right, so in this case, again, setting up Coulomb's law, constant, 9 times 10 to the negative 6 to change it into microcoulombs, and then 4 times 10 to the negative 6. Again, notice I'm not putting in the negative sign for the 4 because I'm just focusing on how big the force is. Now they didn't give us the distance between them, but we can figure that out. It's the whole distance is 12 and the one piece is 9. This is going to have to be 3 centimeters. So we would do 0.03 meters squared. That's going to cause this number to be pretty big. Dividing by a tiny number like this comes out to be 360 newtons. All right, so let's think about the direction of that. This 9 is a positive charge. This is a negative charge, so there's an attraction. They're going to get pulled towards each other. But the charge that I am interested in is this one right here. So it's going to get pulled to the right, pulled toward the other charge. Okay, so you can see that this is a different situation then, because I have 20 newtons to the right and I have 360 newtons to the right. So we're not going to subtract here, we are going to add, because the forces help each other out. And so our answer comes out to be 380 newtons, and they're both pointing to the right. Okay, so this is definitely a type of question that I would suggest you write out, that you're working on paper rather than trying to do this digitally. All right, we're going to look at one more question. There's another way that we can sort of rearrange all these charges. We can into more of a two-dimensional arrangement. Okay, so I sort of bent the line. And we're going to try to find the net force again on the 9 microcoulomb, but the -4 microcoulomb has shifted down to the bottom. And so we're still going to be using the same type of forces. In fact, I'm not going to bother to recalculate that. We're just going to use them. So recall that the 2 microcoulomb and the 9 microcoulomb, they gave us a force of 20 newtons. And then we had the 9 microcoulomb and the -4, and that was that large force, 360 newtons. Okay, so we're same forces that we had before, but the directions are going to be different. Let's look at the 20. So we've got a plus charge and a plus charge. So they're repelling, they're pushing away. I can imagine this red circle moving to the right, getting pushed to the right. Okay, but the other charges, okay, that's an attractive force. We've got positive here, negative here. That means that this is going to get pulled down towards the other one with a force of 360. All right, well, so these forces do not point along the same line. They are perpendicular to each other. So you can't just add or subtract them. You have to use a little bit of trick. So let's recall how we did that before. We built a triangle by drawing one of the vectors and then the other one head to tail. I like to start with the one that's left or right, and then from the end of that arrow I'm going to come down. And so what we're trying to find here is the resultant force, is what we called it before. Resultant force. And we're going to have to find the value, and we're going to find an angle to describe which direction. It's not as simple as just saying, you know, left, right, up, or down. And in fact, the problem encouraged us to use compass directions. So we would use the Pythagorean theorem, 20 squared plus 360 squared, square rooted, to find the magnitude, the overall value of this force. It comes out to be 361. And then we would use the tangent function, or at least that's what I would use, the inverse tangent. So the opposite from the angle is 360, and the adjacent to the angle is 20. And when I do the inverse tangent of that, we get 87 degrees. And if I was going to describe that, I am mainly, my main direction that's right next to the angle is to the east, but I'm south of that. So that's how we describe it, south of east. So a few things to try to remember from previous unit. See what you can do with that.